Right, let's have a look at question 44 first of all. Same as ever, write a little list of what you know. Stone of mass 0.50 kilograms, attached to an inextensible string and whirled in a vertical circle of radius 0.98 and a constant speed of 7 meters per second. I know this is the linear velocity because it's in meters per second. Okay, right, the part I of part A says calculate the angular speed of the stone. So this is omega. All right, look in your data booklet. We don't have omega equals, but we have V equals omega R. So V equals omega R. Omega is V over R. And that's just a simple substitution, obviously. And the answer is in radians per second. There's a unit mark there. So if you didn't get the unit right, you will have lost a mark. It's not meters per second. It's not acceptable to leave a number without the unit. All right. Next bit, A part II. What's the centripetal acceleration? So now we're finding A. And A is V squared over R. So it is 7 squared over 0.98. And that is 50 meters per second squared. Same as before, there's a unit mark there. All right. And then third part of A is the least tension in the string. Right, so for this one, there's a little bit more work here. For this one, we're going to need a diagram. All right. Stone at the top is where the tension is least. Remember that this is the string, and it's tension in the string T that we're interested in for this sort of thing. If it was a roller coaster, it would be R, the contact force there. So the contact force that's acting towards the centre is tension in this case, and it's least at the top. No, remember we talked about the roller coaster. Perhaps the wheels just about, the sense of weightlessness, or the wheels just about leaving the track here. So it's at the top that T is the least. So you've got tension acting towards the centre. The other force you've got is the weight mg. Okay, and both of those combine to make up the centripetal force. So it's T plus mg. Now it's T we're being asked to find. So T equals F, so centripetal force minus mg. Now what is the centripetal force? The centripetal force, if we were to look at this bit here, the centripetal force is that times m. Yeah. So if A is V squared over R, F equals m times A, so it's that times m. So all I really need to do here is, what's m? 0.5 times 50 minus, what's mg? 0.50 times 9.81. Now if you put that into your calculator, you should get, let me just check, 0.5 times 50 equals minus 0.50 times 9.81 is, and we're rounding on to 1 decimal place, 20.1 m for newtons. So there's a bit more work here. I think this is me marking it 2, 2 and 2. But 1 for the answer, 1 for the unit. And the last part, they do actually ask in the question, where in which point in the motion is the tension the least? And it is at the top. So there was another mark for that. A few of you missed this out. You didn't actually state that answer. So that's number 44. Can you watch this again if you need to and correct your answer? Right then, question 45. A plane of mass 0.15 flies so that its centre of mass travels in a horizontal circular path of radius 10 metres. And we're told that the plane completes 2 circuits in 21 seconds. So I've written a little list of what we know, and I've drawn a diagram, not of an aeroplane, just a circle or a rectangle, remember, for a free body diagram. All right, first bit says calculate the angular velocity. So it wants us to work out omega. And remember, omega is in radians per second. So how many radians does it do per second? You know, you can work it out from first principles, but you can also use the equation. Where do we have it? Here. T equals 2 pi over omega, right? T equals 2 pi over omega. Or omega equals 2 pi over T, right? So what do we know? 2 circuits in 21 seconds. What's T? T is the time it takes for 1 circuit. Yeah, so remember your definition and use it. The time it takes for 1 circuit. So if it's 21 seconds for 2, how long does it take to do 1? Well, that will be 21 over 2. So T equals 10.5 seconds. And then we can use omega is 2 pi over 10.5 seconds, and that comes out at 0.6 radians per second. Okay, this people keep going wrong with these. Part B. So make sure. I think I might give you a few more of those to practice. Now we need, it says, the diagram shows a simple frontal view of the plane showing the forces during flight. It assumes there's no sideways force. Calculate the total vertical component. So we need the vertical component of the lift and the horizontal component of the lift. Yeah, so here's the lift force. But we are going to resolve that and replace it with a vertical component and a horizontal component, right? Let me put it on this proper diagram. So here's our vertical component, and here is going to be our horizontal component. All right, we've got no theta there, but what we do know, remember, is that the vertical component is balanced by the weight, and that the horizontal component, of course, is making up the centripetal force, right? So what are we asked? This is part B. We're asked for the vertical component, which is equal to the weight, which is mg. All right, so that's 0.15 kilograms times 9.81, and that is 1.47 newtons. Oops, equals 1.47 newtons. And the horizontal component is equal to the centripetal force, which is, we can't work it out from here, but we have enough information up there. And remember that the centripetal force is mv squared over r. Remember that one? So Actually, can't use that one, can we? Because we don't, well, we could, but it's easier if we use m omega squared r, the other one. All right. So 0.15 times 0.6 squared times, what's the radius of the circle? 10.1, and that is 0.54 newtons. Okay. Okay, last one, question 46, which is one of these trickier examples of motion where the object is circling at an angle. Okay, and the first bit actually says copy the diagram and label, draw on and label the forces. So there's no air resistance, and this is tricky, right? There were 2 marks for this, one for each of the forces, but what I also did was I took off a mark if you labelled, in addition to that, if you added something and labelled it centripetal force. So there's no centripetal force, which is a new force here. Excuse me. Remember what I said, there's tension here, there's weight here, there's all these different forces. One or more of these could provide the centripetal force, all right? So there were, as I said, 2 marks for that, and potentially lost one if you added an extra centripetal force, all right? So yeah, we would have, the next thing that we're potentially going to do is we're going to resolve that tension, which is at an angle, and we're going to resolve it into a vertical and a horizontal component, all right? And to help us out here, Z angles, that's theta, this is theta. And actually, if that's theta, then we know that this is T cos theta, and that is T sine theta, okay? Right, the first question, we don't actually get any data until down here. We're still just talking without calculating. Hence, explain, why is the string not horizontal? Why is the string not horizontal? Why is it there? Well, it's because tension acts at an angle. You know, it is because, so that's the diagram, it's because there's a component that balances the weight, and there is a component that provides the centripetal force. That's why it's not vertical or horizontal. That's why it's circling at an angle. So it's because T provides a component that balances the weight and a component towards the centre of the circle. Alright, so something along those lines. So there's a mark there. Then the next part says, hence give the direction of the resultant force on the bung. Well, the bung isn't moving vertically. These 2 forces are balanced, so there's no resultant vertically. The resultant is horizontally towards the centre of the circle. It's not moving towards the centre of the circle, but that force is keeping it in circular motion. So it's the resultant force is towards the centre of the circular path, and is keeping it. This is the effect it has on the motion, is keeping it at constant velocity or constant speed in the circle. Constant velocity. Alright, and there's your 4. So next up it says, so we're now given some data. We're told that the mass is, let's put this up here. So we've got a bit more room. The mass is 0.06 kilograms. And the length of the string from the boy's hand. So that, the length there is 0.40 meters. And we're told that theta is 75 degrees, right? So there's a little bit more information there. Now we're asked to show that the tension is 2.3 newtons. So that means calculate the tension, right? Now how are we going to do that? Well, do we know that? Yes, we do. We know we can quantify this. We can do m times g. We now know theta. We can work it out. So if we look vertically, if we use the forces that we've got in the vertical plane, we can say, can we not, that T equals 75 equals 0.06 times 9.81. Yeah? T equals theta equal to mg. That's where that comes from. So T is 0.06 times 9.81 over cos 75. And I get 2.27 newtons, which is approximately, 2.3. Now it says calculate the resultant force. So calculating the resultant force, that is the centripetal force, right? So the resultant force is the centripetal force, which is the horizontal component of tension, right? So we now have T theta. We know T. I'm going to use 2.27. But if you haven't done this, this is one of those things where exam boards allow you to get back into the question. So don't give up. There's usually something after a show that question that you can do to get back into the question. So I sine, it's not, it's 2.27 times sine 75, which is, I think it's just 2.2 now, 2.27 times sine 75. Yeah, 2.19 or 2.2 newtons. Okay. And then last off, find the speed of the bung. Unless it says angular velocity, this is asking you for the linear speed, v, right? And v can be calculated, well, what do we know? We know the centripetal force, we know m, we know r, so we can find v. Yeah, if we use centripetal force, because we've calculated the centripetal force, looking at the forces, but now we know F, we know M, we know R, so we can calculate V using this equation here, alright? So if I do, actually let's turn over, if I say F equals mv squared over R, and F was centripetal force, which is 2.27, and M was 0.06, and what's the radius of the circle? It is not 0.4 meters. It is not 0.4 meters. What is the radius of the circle here? So we've got Oh, hang on. Let's read what is now. The length of the string from the boy's hand to the bone. This is the boy's hand. This is the bone. Is 0.40. So we don't need 0.40. We need 75. That's 0.40. We need this angle here. Yeah, we need this angle here. This is what we need to work out for R. Let's call it R. Yeah, we've got 75 here. That's the opposite. That's the hypotenuse. So opposite and hypotenuse. Sine 75 equals R over 0.40. So R equals 0.40 times sine 75, which is 0.40 times sine 75 is 0.39, which isn't far off. Alright, so there's an extra bit of work here. I would suggest that in an exam, if you used L incorrectly, then you would probably gain some marks. So what are we working at? We're working at V, aren't we? We're trying to find V. So we've got 2.27 equals 0.06 using this equation times V squared over 0.39. V squared is, let's rearrange all of this. Okay, and V is square root of 0.39 times 2.27 divided by 0.06, 3.84 meters per second. Okay.